All right, boys and girls, welcome back to the drive-through, a special dinner time version. Sponsored as always by the deli. Hungry? Stop by the deli. Get yourself a baked potato bar, of course. All right, we are back into calculus mode. Welcome back. Hope everybody enjoyed their little break. Okay, we're going to get right into this. Let's find the derivative of our vector valued function given by r of t equals sine of t cosine of t comma t. So this is like half of a helix. Okay, so it's real simple. You just take the derivative of each part, okay? So the derivative of sine is positive cosine. The derivative of cosine is negative sine. And the derivative of t is 1. Okay, so that is our derivative function. Sometimes they will refer to that as the velocity function. Okay, if this is our position function, the derivative is our velocity function. It's also asking us, excuse me, I must have erased that, to find and evaluate the derivative at t equals pi. So r prime of pi is going to be cosine of pi, which is 1. No, that's 0, excuse me. Sine minus sine, so negative 1, and then a 1 here. Okay, so that tells us, if you can imagine our little half helix, okay, climbing around that cylinder, that at this point, at some point, pi, okay, our space curve is not changing at all in the x direction. It's changing by going negative in the y direction. So really, I shouldn't have chosen that point because it's actually the opposite. It would be somewhere over here, okay? And then it's going up in the z direction, okay? Eventually, all of this is going to make more sense when we start getting into examples and we understand that it applies to so much physics. All right, so let's look at all of our little derivative rules. The derivative of a constant. Now, every time in these bolded r's are all, and bolded u, okay, those are all vector valued function. This f, that's just a regular function, okay? A regular function, this f, regular function. Okay, all the bold are vector value functions. Just remember that as you're reading this. So this first rule tells us that the derivative of a constant times a vector valued function is the same thing as that constant times the derivative of the vector valued function. So that same rule holds out. You can pull out constants before you take the derivative of them. The derivative of the sum of two vector valued functions is the same as the sum of the derivatives of two vector valued functions. Okay, I'm not going to read through all of them, but I would like to point out that after number 2, from 3 to 6, these are like our vector valued chain rules. All of those are a variation of the chain rule. Okay, and then the 7th one, we'll get more into that. That one's, I can't even explain it to you right now, so I'm just not going to act like I can. Next slide. All right, let's see if I can actually prove that the derivative of the dot product of two vector valued functions is equal to the first vector valued function times the derivative, dotted with the derivative of the second function plus the second function dotted with the derivative of the first function. This is kind of the dot product chain rule. Okay? I want you to remember that this is a vector valued function, this is a vector valued function, and this is just a regular scalar function, meaning it's an old-fashioned function. Okay? All right, let me try this. First, let me just do some notation. The derivative of r of t we're going to call r prime of t. Okay? So just understand that. You're going to need to kind of look at that. We are also going to let r of t be equal to f of t, we'll call it f1 of t plus g1 of t, and we will say that this u of t is f2 of t plus g2 of t. So let me explain what I mean here. We're working in a We're going to prove this in a plane curve. We're only working in i's and j's. Okay, so sorry, this should be I and j. Oh, that's kind of nice when you change those colors. And that should be I and j. Okay? All right, so before we get started, I want to point one other thing out, and that is r of t dot u of t is equal. This is not calculus at all. Okay? It's going to be, it's a dot product. So the i's and j's are gone. So it's going to be f1 of t times times f2 of t plus g1 of t times g2 of t. That's the definition of the dot product. Okay, so we've got a lot of information. I'm going to go back over it. Notationally, if we take the derivative of this function, we're just going to refer to it as that. We have defined our r of t as f1 of t plus g1 of t. We've defined our u of t as f2 of t plus g2 of t. And we've defined in green here what r of t dot u of t will give us. All right. Well, look, we want to take the derivative with respect to t of this thing right here. Okay? Now look, remember, this is old school. Okay? It's just like a function times a function, but it's two functions. So we're going to apply our old school chain rule. So the derivative of this old school thing here will be f1 of t times f prime 2 of t plus f2 of t times f prime 1 of t. I just said it's first times the derivative of the second plus second times the derivative of the first. Welcome back to calculus! And then, same thing. That thing is old school, so the derivative of that, so this is the derivative of this. That's what this is. Okay, we're just continuing on up. So plus, first, g1 of t times the derivative of the second plus second times the derivative of the first. Alright, so all we did was take the derivative of what you see here in brackets. Okay, now, let me pause this and do some rearranging. Alright, so look, I took what we had and I rewrote the order. Okay, magic. It took me like no time at all, or it took me like 13 minutes while no one was watching, thank God. So, I want you to look real close at this. This is all one big long line of the proof. f1 of t times f2 prime of t plus g1 of t plus g2 prime of t. Well, I can take this highlighted piece here, and what is that? That is, well, look, that is r of t dot g prime of t. Can you see that? It's f1 of t times f prime 2 of t. It's this times f prime 2 plus g1 of t, this times g prime 2 of t. This is r of t, and what is down here? Highlighted in green, well, you probably already know how this movie is going to end. That is G of T, sorry, not G. I'm just using G's. They should be U's. U of T dot R prime of T, and we have just done our first proof of one of the chain rules. Rule number 4, the dot product chain rule. If you didn't catch all that, you might want to watch it again in slow motion. Alright, look, here's our integration rules. Okay, pretty standard. It says if we want to integrate a vector valued function, you integrate each part. Okay? We have definite integrals. This is talking about integrating space curves instead of plane curves, and this is talking about definite integrals involving space curves. Okay? So I pulled these out of your book. You guys are going to need to reference those. Let's keep going with this video. Let's try an example. So, the integral of ti plus 3j with respect to t. Well, that's going to be t squared over 2 plus c. We'll call that c1 I, okay, plus 3t plus c2 j. So, one of the things that we will do is we will just write our c's. We will combine them. But what you need to understand is that this this c is now a vector. It's c1 comma c2. C is equal to c1. Because when we integrated this vector value function, we got another vector valued function. And so instead of adding C1 here and C2 here, we summarize that into C, and C is actually a vector comprised of some components. So let's see if we can do an example here that helps us figure that out. Integration problem with some initial conditions that allow us to find a definitive parent function. So they give us the derivative of r, and they give us some initial conditions. So let's find r of t, okay? The integral of cosine of 2t, oh gosh, u substitution. Okay, that's going to be 1/2, or is it going to be negative 1/2? Let me think, I think it's going to be negative 1/2. No, derivative of sine is cosine, so negative 1/2 sine of 2t, okay? And I'm going to change this over to vector. Nope, I won't. We'll keep working like this. I, okay, minus sine. So that's going to be a plus 1/2 cosine of 2t j. Uh-oh, trig integrals. So we'll have to go to the table for that one. And the integral of 1 over 1 plus t squared is the arctan, okay? And then we've just put a big plus c over there. Okay, remember that this big plus c is really a vector containing 3 numbers. Well, we know that r of 0 is 3i. So if we put in 0 for t, you get r of 0 here. Okay? Well, that's 0. If you put in a 0 here, you get 0. But we need to get to 3. So we know that c1 equals 3. Do you see how I did that? Okay? Here, r 0, you get 1/2 of 2 times 0, you get 1/2 of 1. Oh, hold on a second. I just did something wrong here, okay? Look, these are different. This is not right. So the integral of negative 2 sine of t should just be 2 cosine of t. Okay, you see what I did there? I read these as the same exact thing, and they're not. So let's go back to that. If we put in a 0 for t, cosine of 0 is 1, and 2 times 1 is 0. So r of 0 is 2 plus c2. However, r of 0 is negative 2. So our c2, okay, must be negative 4. Okay, now if we put in a 0 for the arctan, let's see, tangent of 0, you get 0, okay? So r of 0 equals 0 plus c3. Well, we know that r of 0 is a 1. That's a 1 there. So we can say 1 is 0 plus c3. So c3 is 1. So that means that our parent function, r of t, must be 1/2 sine of 2t plus 3I plus 2 cosine of t minus 4j plus the arctan of t plus 1j. Legitimately winded at this point. Is there more? No. Boom!